Okay, in this lecture video, we're going to talk about how we describe the sigmoidal binding of hemoglobin to oxygen using the Hill equation. And so what we're talking about here is relating, like we did with myoglobin, the fractional saturation of hemoglobin to the KD, the affinity of hemoglobin for oxygen, its ligand. So if we're going to do that, first let's write our dissociation expression. So we're talking about hemoglobin, which is bound to 4 molecules of oxygen, breaking down into hemoglobin, so that's the tetramer, and 4 individual oxygen molecules. And this will be good for any sort of molecule that's going to undergo this cooperative binding or the binding of multiple ligands. So we could write a more generalized equation. So there's some protein ligand complex where there are N ligands, L stands for ligand, bound to the protein. So the dissociation would be the protein plus N number of ligands, where N is the number of binding sites. So we're going to do this again for hemoglobin, but you can make it really general. So if we wanted to write the KD then for this expression, the KD would be equal to products over reactants, the concentration of hemoglobin, times the concentration of oxygen raised to the 4th power, the coefficient in the chemical equation, divided by the concentration of the complex, which is the reactant side of the equation. And then we're going to use this KD and we're going to start substituting in to the fractional saturation equation using our KD. So we know that the fractional saturation of hemoglobin would be the binding sites occupied, which would be 4 times the concentration of the complex, because there are 4 binding sites. So 4 times the concentration of whatever that tetramer is when it's got oxygen completely bound, so that's a 4, by the way, divided by the total number of binding sites available. So that would be 4 times the concentration of hemoglobin unbound plus the concentration of hemoglobin bound to oxygen. So just like with myoglobin, we're going to substitute in for the concentration of the complex using our expression for the KD value. So we know that the concentration of the complex is going to be equal to the concentration of hemoglobin times the concentration of oxygen to the 4th power divided by the KD. So I got that by rearranging my KD expression. So if I substitute that in, I get that the fractional saturation of oxygen to hemoglobin is equal. So I've got this huge part now for my numerator where I've substituted in for the concentration of the complex divided by the concentration of hemoglobin plus, again, substituting in for the concentration of the complex divided by the KD. Then we can factor out, so I'll just write down the math I would do, factor out the concentration of hemoglobin. This is the same math that we did with myoglobin's expression. Then we would multiply by the KD over the KD, so multiplying by 1, and then we would cancel out the concentration of hemoglobin. And when we were all said and done, we would find the concentration of theta, fractional saturation of oxygen, is the concentration of oxygen to the 4th power divided by the KD plus the concentration of oxygen to the 4th power. So if we made a more simplified expression, we would find that the concentration, or the fractional saturation of some ligand to a protein, whatever that ligand and protein is, would be the concentration of ligand raised to N, the number of binding sites that it will stick to, divided by the KD plus the concentration of ligand to the N value. And this equation here is called the Hill equation. And this describes the saturation of a multi-subunit protein as a function of ligand. So the saturation of a protein that can bind multiple ligands. Okay? The N value, this right here, that is the Hill constant. And the Hill constant, or coefficient, as it's sometimes referred to, describes the degree of cooperativity. So if the Hill constant is equal to 1, that binding is described as non-cooperative. There is no cooperation taking place. And if you were to plot that, you would get a hyperbolic curve. So in our equation, if N was 1, that equation would reduce to the same saturation equation that we saw for myoglobin. If N is greater than 1, now we have positive cooperativity, which is what we see with hemoglobin. That means the binding of one ligand is going to enhance the affinity of the protein for the rest of the ligands. And bindings, N values less than 1 mean negative cooperativity, which is the opposite, and that's kind of weird. So we're talking about where the binding of one ligand reduces the affinity for the binding of the others, and this is not as well documented of a case. So you can do some more math to the Hill equation so that you can really represent it graphically, so you can figure out for some protein binding to ligand or ligands what N really is, as well as the KD value. So you can do some math and end up with an expression that looks like this, where you have the log of the saturation of ligand over 1 minus the saturation of ligand equal to N times the log, the concentration of ligand, minus the log of the KD value. So that's just doing some math to our Hill equation. And when you look at this, what you should see is the equation for a straight line. So y is equal to, and then we've got our x value, which would be the concentration of ligand. So you're plotting y versus the concentration of ligand, which means that we have N as the slope. Sorry, I should have included the log there. N as the slope of that line, and minus the log of the KD as our y-intercept. So y equals mx plus b. So we could look at that representation graphically. Figure 5-14 in your textbook, and this lets us calculate a true value for N. And what we see here in particular for hemoglobin is that that N value is actually 3. But you say, wait a second, I thought N was equal to 4. There are 4 binding sites, 1 per molecule, and hemoglobin is a tetramer. So when N is less than the total number of sites for theoretical binding, it just really reflects the interactions between the sites and ligands. So it just means that it's not complete cooperativity. If N would be equal to 4, it would mean that all the sites would bind simultaneously. There would be no partially saturated molecules. That would be perfect cooperativity. So an N value of 3 just means that it's not perfect. And what you can see here is you can have these straight lines for the 2 separate states of hemoglobin, the high affinity oxygen state and the low affinity oxygen state, which would each have N values of 1 for that particular state.